Okay, next we're going to go back to Tim Livengood, who will be speaking about submillimeter solar observation, lunar volatiles experiment at the South Pole.
Hello again. The instrument name is pronounced either SOLVE or SSOLVE, depending on who you are on our experiment team. Next slide, please. All right, the goal for SOLVE is to measure water vapor in the lunar exosphere from the surface to space. As I mentioned in the Sniffler talk, we have observations of hydration in the surface and apparent diurnal variability that seems to suggest motion over the surface, but very wide range of possible abundances, including well below the quantity required for a surface-bounded exosphere as an upper limit. Uh, and so we want to be able to measure pretty much all the range that matters. And so the method will be to look at spectral absorption features in water and OH. And as a bonus in the spectrum we're using for water, we will also be sensitive to HDO if we should happen to have a fairly large amount of material. But H2O and OH are the primary goals. We'll have a high dynamic range in the submillimeter range between as low as 10 to the fifth molecules per cubic centimeter of water in volume density near the surface, or no upper limit on that. The goal is to measure the diurnal variability of any gas that we have, well, diurnal or according to any other time scale. While we're at it, by measuring the spectral absorption, we also get information on the kinetic temperature of the gas molecules from the broadening of the line shape. And as I mentioned, if we're so fortunate as to have a relatively large amount of water, then in principle we can measure HDO as well. Next slide, please. So we have an eye chart as a science traceability matrix. In our first few minutes of operation on the lunar surface, we'll establish the most fundamental question: is it really a surface-bounded exosphere or not? Our signal to noise is good enough that within a second, we'll have signal to noise of about 7 on the upper limit for a surface-bounded, that would be a surface-bounded exosphere. And we'll simply nail that question once and for all, at least for the water molecule. We need to discriminate lunar water from any contaminant water that would come with the spacecraft. This is a common problem, for example, with mass spectrometry methods. So we have an internal calibration target to measure water vapor that is within the instrument itself. Of course, we'll try to eliminate that, but the idea here is to calibrate for imperfection. And also to look at the neighboring lunar surface to measure absorption between us and the surface, so that we can measure outgassing from the spacecraft itself, from fuel implanted into the
Two
surface, and
minutes,
so on.
Tim.
Okay.
Minutes. Yep.
And then over the wide range of possible abundances that we can measure, that will help to discriminate whether the water we're looking at is indigenous or exogenous water based on abundance. That the exogenous sources have limits on how much they can supply, and if we have more than that, then you can rule out a possible goal. We'll skip the other parts here for now. Next slide, please. Okay, we're just beginning our second year of funding under DALI. We are preparing to prototype. We're going to use a heliostat with an elevation azimuth mounting for our instrument, as you can see here. A sun sensor to locate the sun. We have an elevation axis that you see here, and this box sits on top of an azimuth axis so that we can deploy anywhere on the surface of the moon. For this particular workshop, the South Pole is a strong goal, but we could be anywhere on the moon and make our measurements with the same instrument, measuring simultaneously between our 530 gigahertz and our 2.5 terahertz receivers. Next slide. This is an example of the absorption lines that could be seen on water, where that's the smallest one of those is the upper limit for a surface-bounded exosphere. Next slide, please. And then using that as the largest amount, we could go well below by a couple orders of magnitude below the density of a surface-bounded exosphere, and still measure a line until we get down to about 10 to the 12 molecules per square centimeter, at which point we really have to start adding up multiple measurement intervals in order to get enough signal. Next one, please. Similarly, for OH, we can measure it, even small quantities of OH, in just a few minutes. And so this puts us in a strong position to measure diurnal or any other timescale variability of water vapor or OH over the lunar surface. And next one, please. And this is just our concept of operations. We sit on the surface, we look at the sun, we track the sun, and we see how much is between us and the sun, with the color bands below showing in cartoon fashion how different measurement methods have seen the pattern of water in the lunar surface.
We're 30 seconds over.
Okay, then I'm all done.
Well, now you can give your conclusion slide.
Nope, that I intended to end here. That's an extra.
Okay.
In case somebody asks later.
Okay. All right. Sorry.